Hello everyone, welcome back. In this video, we're going to talk about the transcendental functions and some of the properties that they have. So we'll first start with the trigonometric functions. So here are the graphs of the sine and the cosine function. And for both of the sine and the cosine functions, the domain is all real numbers, and the range is the closed interval from -1 to 1. So the smallest values that the function can reach is -1, and the largest value that it can reach is +1. So we have these inequalities. So for both the sine and the cosine functions, they are greater than or equal to -1, but less than or equal to +1. So we can also write this equivalently using the absolute value function. The absolute value of sine and cosine has to be less than or equal to 1. Now the zeros of the sine function occur at every integer multiple of pi. So for example, at 0, pi, 2 pi, 3 pi, 4 pi, and so on, the zeros of the function occur at these x coordinates. Now the zeros for the cosine function occur at every integer multiple, but shifted by pi over 2 radians. So at pi over 2, the cosine function is equal to 0. And if you were to add any integer multiple of pi to this coordinate, then we get zeros of the function. So pi over 2 plus pi is 3 pi over 2. And if we add another pi, that gives us 5 pi over 2. And so the zeros for the cosine function is going to be at pi over 2 plus any integer multiple of pi. So we can write this using this notation. So the zeros of the sine function occur whenever x is n times pi, where n is an integer. And we use the z symbol to denote integers. And for the cosine function, this will be equal to 0 whenever x is an integer multiple of pi, so n times pi, but we also add this pi over 2 as well. Now the sine and the cosine functions are periodic functions and have a period of 2 pi. So this means that for all values of x, the sine of x plus 2 pi is the same as the sine of x, and the cosine of x plus 2 pi is the same as the cosine of x. So if we look at the graphs of, say, the sine function, so if we were to look at the graph between -pi and pi, this has a length of 2 pi, and the graph between pi and 3 pi will also have a length of 2 pi. And we see that this graph of the function starts to repeat itself at every 2 pi multiples. So the sine and the cosine functions are both periodic and has a period of 2 pi. So next we will introduce the exponential functions. And the exponential functions are functions of the form f of x is equal to a to the power of x. So the base a is any positive constant, and the domain of the function is all real numbers, and the range is all positive numbers, so from 0 to infinity. So what this tells us is that the exponential functions can never be negative, and it can also never be equal to 0. So here are some examples of the graphs of exponential functions. Over on the left, we have exponential growth functions, and these occur if the base is a number that's larger than 1. So for example, we have the exponential function 2 to the power of x, 3 to the power of x, or 4 to the power of x. And over on the right, we have examples of exponential decay functions. And so these functions occur if the base is a value that's smaller than 1. So for example, we have 1/2 to the power of x, 1/3 to the power of x, and 1/4 to the power of x. So these are fractions that are smaller than 1. So we have exponential decay functions. Now notice that the exponential functions all have a y-intercept at 1. So why is that the case? Well, let's have a look at calculating the y-intercept. So if our function is a to the power of x, and we want to locate the y-intercept, recall that if we want to find the y-intercept, we're going to let x be equal to 0, and then we're going to solve for y. Oops. So if I let x be equal to 0, then the exponential function will be a to the power of 0, and anything to the power of 0 is equal to 1. So this tells us that the y-intercept occurs at 0, 1. So now we'll introduce logarithmic functions. So these are functions that take on the form log base a of x, where the base a is a positive constant, and these functions are the inverses of the exponential functions. So there is a relationship between exponential and logarithmic functions. So over on the left, we have examples of increasing logarithmic functions. So these are functions that will increase as x gets larger. And this happens if the base a is a value larger than 1. So for example, we have log base 2 of x, log base 3 of x, and log base 4 of x. Over on the right, we have examples of decreasing logarithmic functions, and these occur if the base a is less than 1. So we have 1/2, 1/3, or 1/4. Now it may be useful to create a new function from two other functions. This is called a composite function, and we use a symbol with a circle to denote the composition with f and g. So the composite function is defined as follows. We take f and evaluate it at g of x. Now the domain of the composite function is the set of all x in the domain of g, such that g of x is in the domain of f. So the composition is defined whenever both g of x and the composite function are both defined. So now we're going to look at some of the properties of both the exponential and logarithmic functions. I mentioned earlier that the exponential and the logarithmic functions are inverses of each other. And there's also going to be a few special types of functions that we will define. And these are called the natural exponential and the natural logarithmic functions. So here I've listed some laws of exponent, which will help us simplify certain expressions. So the function e to the x is called the natural exponential function, where e is roughly 2.718. Now there is a reason why we choose e to be this number, and the explanation of why we choose e to be this constant will be explained in the next chapter. But for now, just know that we define the natural exponential function where the base e is given by this number here. So the next definition is going to be on inverses. So if we have a function f with a domain d and a range of e, then its inverse function f inverse has the domain e with the range d. And it's defined by the following relationship. So f inverse of y is going to be equal to x if and only if f of x is equal to y for any y in E. So on the left we have our function that takes the set D and maps it to the set E. Now the inverse function works in the opposite direction. So it's going to take the values of E and sends it back to the set D. So the function sends the number 1 to the number 1 in the set E. Then the inverse function will take the number 1 from the set E and sends it back to the original value, which was 1 in the set D. Similarly, since the function takes the number 2 and maps it to the number 4. The inverse will take the number 4 and maps it back to the number 2. And similarly, we have the function f taking the number 5, mapping it to 25. The inverse will take 25 and map it back to the number 5. So note that we have the following relationship between the domain and ranges of these functions. The domain of the inverse function is going to be the range of f, and the range of the inverse function will be the domain of f. So the inverses will have these cancellation equations. So f inverse of f of x is equal to x for every d in x. So you can think of f inverse and f canceling each other, leaving you with x. Similarly, we have f of f inverse of x, which also gives you x for every x in the set E. And the graph of the inverse function is obtained by reflecting the graph of f above the line y equals x. So in this diagram here, we have the exponential functions on the left, so y equals 2 to the x, 3 to the x, and 4 to the x. Now the line y equals x is this straight line through the origin. And if we were to reflect about this line, then we obtain the inverse functions. So recall that the logarithmic functions are the inverses of the exponential functions. So y equals log base 2 of x is the inverse function of the exponential function y equals 2 to the x. Similarly, log base 3 of x is the inverse of 3 to the x, and log base 4 of x is the inverse of 4 to the x. So if we were to use the formulation of the inverse functions, then we have the following equations. So log base a of y equals x is the same as a to the x equals y. And we have the cancellation equations. Log base a of a to the power of x is equal to x, where x is any real number. And a to the power of log base a of x will be equal to x for any x that is a positive number. Now here are some laws of the logarithms. So if x and y are any positive numbers, then the log base a of xy is the same as log a of x plus log a of y. If I have the log base a of x divided by y, then this can be turned into a subtraction, so log base a of x minus log base a of y. And the third property, we have log base a of x to the power of r is equal to r times log base a of x, where r is any real number. So the exponent on the x can be multiplied in front of the logarithm. Now, just like we define the natural exponential function that has a base of e, we can also define the natural logarithm. So the logarithm that has the base of e is called the natural logarithm, and it has its own special notation. So log base e of x is shorthanded to ln of x, or the ln of x. Now we can apply the same inverse formulation to obtain the following properties for the natural logarithm. Okay. So lastly, we have a change of base formula. So this allows us to change a logarithm that has any base of a to the natural logarithm. And the formula is that the log base a of x is equal to the ln of x divided by the ln of a. So let's have a look at a few examples. So let's find the domain of the function, the square root of 2 minus x divided by x minus 1. So here there are two things that we need to consider. One is going to be the square root of 2 minus x, And the other is the denominator of f of x, which is x minus 1. So let's first start with the square root of 2 minus x. Now for the square root function, to be defined, we require that 2 minus x has to be greater than or equal to 0. Okay, so we can't take the square root of a negative number. So everything that's underneath the square root must be greater than or equal to 0. So we'll set 2 minus x greater than or equal to 0 and then solve for x. So here we have 2. If we add x to both sides, we get 2 is larger than or equal to x. And then we can rewrite this so that the x is on the left-hand side. So we can swap the inequality around. So we have that x is less than or equal to 2. So that is one condition for f of x to be defined. And the other is that we cannot divide by 0. So f of x is undefined if the denominator, which is x minus 1, is equal to 0. So then we need to solve for the equation x minus 1 equals to 0. So we have that x is equal to 1. So the function's undefined if x is equal to 1. So we need to exclude 1 from the domain. So here what we could do is draw a number line. So we found that x can be less than or equal to 2, but x cannot be equal to 1. So here we can shade in the value of 2, but we have an open circle at 1, and x can be any number that is smaller than 2. And so this tells us that the domain of the function is going to be from negative infinity to positive 1 with open brackets, union, we have an open bracket at 1 to 2, but we can include the value of 2, so we have a square bracket. Now in the next example, we'll look at finding the composite functions. So we're given that f of x is equal to the root of x squared plus x plus 1, and g of x is 3x minus 1. We want to find the composite functions f composed with g and g composed with f. So the composition of f and g is f of g of x. So to find the composite function, we will first look at g of x. So we know that g of x is equal to 3x minus 1. So we're going to substitute that into our composite function. So we have f of 3x minus 1. And so now we want to evaluate f at 3x minus 1. So our f of x is the square root of x squared plus x plus 1. So wherever we see an x in our function, we're going to replace it with a 3x minus 1. So we have that square root of 3x minus 1 squared plus 3x minus 1 plus 1. So now we can simplify our function. So 3 minus 1 squared, we can FOIL. So we end up with 9x squared minus 3x plus 1 plus 3x minus 1 plus 1. So now we'll simplify. So the negative 3x's can cancel with the positive 3x. The positive 1 can cancel with the negative 1. So we have the square root of 9x squared minus 3x plus 1. So that is f composed with g. Next, we'll look at g composed with f. And this is defined to be g of f of x. So here we look at substituting our f of x. So our f of x is the square root of x squared plus x plus 1. So this will be equal to g of the root of x squared plus x plus 1. And now we want to evaluate g at the square root of x squared plus x plus 1. So wherever we see the x in the function g, we will replace it with the square root of x squared plus x plus 1. So we have 3 times the square root of x squared plus x plus 1 minus 1. And so this is our g composed with f. So for number 3, we're going to look at evaluating logarithms. So for the first one, we have log base 5 of 125. Okay, so we can write this equivalently in exponential form. So if we call this number x, then what we can do to solve for this logarithm is write it so that we have 5 to the power of x is equal to 125. So what exponent on 5 gives us 125? Well, if x is equal to 3, then 5 to the power of 3 is equal to 125. So the logarithm of base 5 of 125 is equal to 3. Now for b, we have log base 3 of 1 over 27. So again, if we call this number x, then the equivalent form is 3 to the power of x is equal to 1 over 27. So what power on base 3 gives me 1 over 27? Well, if x is equal to negative 3, then 3 to the power of negative 3 is equal to 1 over 3 to the power of 3, right? So we can write negative exponents as a reciprocal. And 3 to the power of 3 is equal to 27. So the exponent on base 3 that gives us 1 over 27 is negative 3. So this tells us that the log base 3 of 1 over 27 is negative 3. Now for part C, we have the natural logarithm of 1 over e. So let's call this x and write it in the equivalent form. So we have e to what power of x gives me 1 divided by e. Well, if x is equal to negative 1, then e to the negative 1 is 1 over e. So the natural log of 1 over e is equal to negative 1. And lastly, we have log base 10 of the square root of 10. So if we call this number x and write it in exponential form, then we have 10 to the power of x is equal to the square root of 10. So what power on base 10 gives me the square root of 10? Well, if x is equal to 1/2, then 10 to the power of 1/2 is the same as the square root of 10. So this tells us that the log base 10 of the square root of 10 is equal to 1/2. Now in the fourth example, we have the natural log of 5 plus 5 times the natural log of 3. And we want to express this as a single logarithm. So we're going to need the laws of logarithms to simplify the expression. So let's first deal with the second term. So we have 5 times the natural log of 3. Well, we can write this as the natural log of 5 plus the natural log of 3 to the power of 5. So here we're using the third law to rewrite the coefficient in front of the logarithm as an exponent on the number 3. So now we have the the natural log of 5 plus the natural log of 3 to the power of 5. And since we're adding logarithms, we can use the first law to write it as a single logarithm by multiplying what is inside both of these logarithms. So we have 5 times 3 to the power of 5 by using the first law. And if you were to perform this calculation, this would be the natural log of 1,215. Now in the next example, we have the natural log of a plus b plus the natural log of a minus b minus 2 times the natural log of c. So let's simplify this expression so that we can write it as a single logarithm. So let's first deal with the third term. So we have the coefficient of 2, and if we were to use the third law, we can move the coefficient as a power on c. So we have the natural log of a plus b plus the natural log of a minus b minus the natural log of c squared. And now if we use the first law on the first two terms, we can combine these as the natural log of a plus b times a minus b, and then we subtract the natural log of c squared. This is using law 1. And then we can use the second law to rewrite the difference of logarithms. So the natural log of a plus b times a minus b divided by c squared and this is using the second law.